This is the Mathematics Education Podcast from mathedpodcast.com.
Welcome to the Math Ed Podcast. My name is Chuck Munter, an assistant professor of mathematics education at the University of Missouri and a new contributor to the podcast. This year we've decided to create a new kind of episode to periodically include in the podcast feed, one that is more of a digest of several recent research studies rather than an in-depth interview focused on just one study. This new format is modeled in part after the old journal Investigations in Mathematics Education. Published quarterly from 1968 to 1988, that journal offered expanded abstracts and critical analyses of recent research. To help translate that idea into podcast form, we extended an invitation to all listeners to become contributors, who submit brief summaries and interpretations of recent works that they are interested in. In this second digest episode, we offer 3 such summaries. First, Jeremy Strayer will describe a recent study by Pat Thompson and colleagues on covariational reasoning among U.S. and South Korean secondary mathematics teachers, published in the December issue of the Journal of Mathematical Behavior. Next, Kimberly Morrow will summarize Joanne Lobato and C. David Walters' chapter in the new Compendium for Research in Mathematics Education on approaches to learning trajectories and progressions. Finally, Sam Otten will summarize an article from the January issue of Early Childhood Education Journal by Drew Polly and colleagues on the influence of professional development along with school-level and teacher-level variables on the mathematics achievement of primary students. We hope you enjoy this second digest episode and welcome suggestions and contributions from listeners.
I'm Jeremy Strayer from Middle Tennessee State University, and I'm going to share a summary of Patrick Thompson, Neil Hatfield, Yoon, Surani Joshua, and Cameron Byerley's article, Covariational Reasoning Among U.S. and South Korean Secondary Mathematics Teachers. It was recently published in the Journal of Mathematical Behavior, Volume 48. This work was funded by the National Science Foundation, and it is part of a series of studies that investigate U.S. high school mathematics teachers' mathematical meanings for teaching. The authors begin by building a case from both the literature and their own experience. They note that despite the fact that covariational reasoning is key for building deep understandings of many mathematical concepts, reasoning covariationally in U.S. mathematics classrooms is uncommon, both for school and university students and for high school teachers. So, is this state of affairs unique to the U.S.? Well, the authors noted that an international comparison of elementary school textbooks suggested that while the U.S. provides little attention to covariation between two quantities, there are non-U.S. countries that explicitly address covariation, and some of them as early as the 4th grade. So, this study sought to fill a gap in the literature by investigating covariational reasoning internationally with a large, geographically diverse sample of teachers. The researchers included 366 middle and high school teachers from South Korea. This is a country that addresses covariation explicitly in its school mathematics curricula and where the middle and high school math teachers take the same credential exam. They also included 121 high school teachers from the U.S. The authors sought to understand 3 things. First, how do the secondary math teachers in their samples reason covariationally about dynamic phenomena that they witness? Second, are there differences between U.S. and South Korean teachers in the sample with regard to covariational reasoning? And third, is it necessary to create a multiplicative object of two quantities' attributes in order to reason covariationally? We will say more about this third point in a moment. To answer these questions, the research team created a task that used an animation that showed the changing values of two quantities. This animation showed the simultaneous variation of the quantity's values by representing the variation of one of the quantity's values with a vector on a vertical axis, and the variation of the other quantity's values with a vector on a horizontal axis. The teachers watched the animation multiple times, and then they were asked to sketch a graph of the value of one quantity relative to the value of the other quantity. You can find a link to the animation and more information about this task in the article. Once the teacher graph data were collected, it was scored based first on the teacher's correct placement of the initial point of the graph, and second, on the correct overall shape of the graph. So what did the researchers find? The data showed that mature covariational reasoning was present in both the US and South Korean samples, but it was present with a frequency that is less than we would hope for. Second, the South Korean teachers did score significantly higher than the US teachers. The authors note that this difference suggests that difficulty with covariational reasoning is likely a cultural artifact of educational systems and not just because it's a hard thing to do. Finally, the data showed that creating a multiplicative object of the quantity's attributes plays an essential role in reasoning covariationally. This means that for teachers to have placed the initial point correctly, they needed to unite the two quantities' values into a multiplicative mathematical object. And then, in order to sketch a correct graph, they needed to maintain that unity as they tracked the simultaneous variation of their values in the animation. I want to close this commentary by noting that this article has a lot to offer both experienced and novice math ed researchers. First, the authors succinctly situated the study within decades of research on an established topic, and they referenced both recent and seminal works along the way. Second, they clearly described how the team created and scaled up a task used for their research. This process included conducting interviews, piloting, returning to the theory that motivated the task, adjusting the task, then piloting some more, and, well, there are more steps. If you're interested in this aspect, be sure to read the article. The team also utilized multiple statistical methods, and they helped the reader understand how the results, effect sizes, and probability of superiority scores should be interpreted in this particular research context. Finally, the authors made claims that are helpful for the field, but that did not overreach. Using the same data, I could imagine some researchers trying to make some grand generalized claims about South Korean teachers being better at covariational reasoning than US teachers. However, these authors always stayed within their data. Furthermore, they were thorough with regard to limitations. For example, they provided a discussion of their confidence in the representativeness of the samples. They were open about the ways that teachers could have potentially circumvented the intent of the task. And they explained some fine-grained design decisions they had to make, such as why they had the animation vary one quantity at a constant rate. If you are in agreement that mathematics instruction must explicitly help students build understandings of how graphs represent the simultaneous variation of two quantities, then you will definitely want to check this article out.
What's the difference between a learning trajectory and a learning progression? Ask 100 educators this question and you will get 100 different answers. My name is Kimberly Morrow-Leong. In this month's podcast, we will review Joanne Lobato's and C. David Walter's chapter, A Taxonomy of Approaches to Learning Trajectories and Progressions, in NCTM's recently published Compendium for Research in Mathematics Education. Scholarship in the area of learning trajectories and progressions has expanded, and the potential for influencing curriculum and policy continues to grow. Crafting a common definition of learning trajectories and learning progressions, according to Lobato and Walters, has been a broad goal in the existing literature. However, after conducting a comprehensive literature review of learning trajectories and progressions, while intentionally including work in the area of science education, Lobato and Walters found a variety of significantly different approaches. These differences have not been previously identified, but are critically important in guiding future research. Clearly articulating assumptions on a variety of dimensions can have meaningful impact on research design and communication. Much of the rest of the article describes a taxonomy of 7 approaches to learning trajectories or progressions. The differences in approaches are not captured by the term, quote, learning trajectory, end quote, which is typically used by mathematics educators, versus, quote, learning progression, end quote, which is typically used by science educators. Instead, the differences cut across disciplinary boundaries. Therefore, trajectory and progression are used interchangeably in Lobato and Walter's chapter. From this point on, we will use the acronym LTP, spelled LT/P, in order to remember that the two terms are not differentiated. After coding a wide variety of articles from both science and mathematics education, the authors settled on a list of 7 approaches to LTPs that is short enough to be useful, but whose individual categories are broad enough to be inclusive. Following the structure of the chapter, each category will be described here. Some features will be described, and some of its benefits and trade-offs will be highlighted. Approach number 1, cognitive levels. The Van Healy hierarchy for geometry is included in the cognitive levels approach category. Batista's LTP for measurement is another familiar example. Featuring qualitative categories, all LTPs in the cognitive levels category have a beginning stage, and students move towards an ending level. Characterizing the levels might include milestones that students reach, or they may be identified by students' misconceptions. Since the goal of a cognitive levels LTP is to diagnose a student's current level, the initial research of this kind of LTP often begins with a cross-sectional interview over multiple grade levels in order to identify the full range of levels. A benefit of this form of LTP is the power to diagnose student progress, which can be used formatively. On the other hand, a major criticism of this kind of LTP is that it does not focus on the learning mechanisms themselves, but this is primarily because the cross-sectional interview methodology does not seek to uncover the learning mechanisms. Approach number 2, levels of discourse. The levels of discourse approach is a different conception of an LTP. Rather than focusing on mathematics, the levels of discourse LTP tracks the level of sophistication of an individual student's discourse. Many of the examples cited come from science education, but some LTPs reference Toulmin's argumentation model, which will be familiar to mathematicians. Levels tend to be characterized by what a student can do, rather than what they cannot do. Categories also tend to be very broad, describing how students move from primary, otherwise known as familiar or home language, to secondary language, which is the language used in social institutions like school. Approach number 3, schemes and operations. The LTPs which come from a schemes and operations approach come out of the theoretical tradition of Piaget, in which the scheme and the construction and modification of schemes plays a central role. Most research is conducted within the teaching experiment format and focuses on a microanalysis of one student's mathematical understanding. Identifying and articulating individual student schemes is vital to the research design. But one drawback is that there is less attention paid to the actions of the teacher. Another drawback is the relatively small number of students who have been subjects in this research design, which limits its generalizability. The greatest contribution of the research done in these kinds of LTP is the highlighting of constructs that are useful for others. Familiar researchers include Steffi, Olive, and Norton in fractions, Hackenberg in algebraic reasonings, Moore for trigonometry, and Tillema in combinatorial reasoning. Approach number 4, hypothetical learning trajectory. The hypothetical learning trajectory approach, or HLT, turns the focus to include the actions of the teacher. The term was originally coined in Simon's 1995 article as a model of teachers' decision-making, but later became a frame to highlight the coordination between levels of student thinking and instructional tasks that support students' movement through those levels. Clements and Sarama have designed LTPs in the areas of number and operations, measurement, and geometry that are of this approach. One of the features of these LTPs is that the HLT is dependent on the tasks that are selected, which requires teachers to continually seek new information about students, effectively co-constructing student learning. Despite the interpretive nature of HLT, research on LTs includes careful task design, and data is collected in order to construct a general HLT. The power of this approach lies in its ability to serve as a resource for teachers. One trade-off is that the instructional support most often highlighted is that of the tasks, and less, though, the students' learning processes. Approach number 5, collective mathematical practices. The previous 4 approaches capture the growth of mathematical understanding or discourse at the individual level. The 5th category of LTP characterizes the development of an entire classroom collective. In these LTPs, classrooms of students have a personality that emerges. There are a number of studies that have identified the collective behavior and progress of whole classes of students, including studies on arithmetic, integers, place value, statistics, and undergraduate mathematics classes as well. The documenting collective activity method of gathering data, or DCA, includes generating a log of student argumentation, describing a norm of behavior for that class, and finally identifying when an argument comes to be, quote, taken as shared, end quote. One of the potential concerns is that LTPs in this approach assume a classroom that is engaged in inquiry-based instruction. The primary benefit may be that these LTPs embrace a class as a whole, much as teachers do. Approach number 6, disciplinary logic and curricular coherence. The best-known LTPs in this category are the progressions produced by the Common Core writing team, otherwise known as the progressions documents. Features of the LTPs in this category are the broad stretches of years that are covered by the LTP and the fact that they draw on published standards. Their chief role is to inform curriculum and textbooks and provide touch points for assessments. These LTPs are also typically written to address a broader audience of readers, such as principals, parents, and policymakers. One of the disadvantages of the LTPs of this approach is the potential to cherry-pick tasks or concepts from different research projects that are not complementary. This can lead to important conceptual ideas brought up but not developed. The LTPs of the disciplinary logic approach are informed by research, which is not the same as being based on research. As the name implies, research data about student learning inspires but does not direct the development of these LTPs. Instead, the logic of the discipline and discipline experts determine the sequence of instruction. Approach number 7, observable strategies and learning performances. In this approach, levels in the LTP are described as observable student behaviors, such as their mathematical strategies, rather than as inferences about the student conceptions. One example comes from the Vermont Ongoing Assessment Project, which uses several exemplars of student work to illustrate 3 or 4 levels of strategies. The key benefit of the LTP in this approach is a certain comfort level for teachers. Student strategies tend to be more familiar to teachers than inferred cognitive conceptions or mental schemes might be. Furthermore, while cognitive categories offer sometimes vague descriptors, the LTPs in this approach are not vague. That clarity, of course, is the origin of one of the key drawbacks. The trade-off with LTPs of this type is that they tend to overlook how a single conception may give rise to several strategies, and how a correct performance does not always guarantee a solid conception behind it. If you'd like to learn more about learning trajectories and learning progressions, be sure to read the final section of this chapter. The authors first address the validation of LTPs in the research literature, and then consider research on the use of LTPs with teachers. The chapter wraps up with a review of some of the critical observations made on LTPs, including the lack of attention to cultural heterogeneity and the inclusion of local epistemological perspectives. The authors also call attention to the criticism that LTPs are typically expressed as linear and knowledge is progressing neatly through levels, in contrast to the landscape or network conception of learning. In conclusion, the author's words state the purpose of this chapter best. By drawing attention to the advantages and trade-offs of each approach, we hope to advance a conversation that leads to a next generation of approaches to LTP research.
I am Sam Otten from the University of Missouri, and I'll be summarizing an article titled The Influence of Mathematics Professional Development, School Level, and Teacher Level Variables on Primary Students' Mathematics Achievement. It was just published in the Early Childhood Education Journal, Volume 46, and it was written by Drew Pauly, with Wang, Martin, Lambert, Pugalee, and Middleton as co-authors. The article focuses on formative assessment as an aspect of instruction that we know is consequential for student learning. It reports on an effort to help kindergarten and first grade teachers develop their formative assessment practices through a year-long professional development experience. The professional development was rooted in the notion of learner-centered PD, which means that it was sustained and focused on student learning around specific content. It involved the teachers in a hands-on way, and it provided follow-up through classroom support or workshops. So the main goal of the study was to investigate how this year-long PD on formative assessment related to the K-1 teacher's instruction and to student achievement. The researchers also considered school-level and teacher-level characteristics as they examined the relationship between the formative assessment practices and the student achievement data. The formative assessment PD made use of AMC Anywhere, which is an online formative assessment system. AMC stands for Assessing Math Concepts, and it's a tool where the teacher can complete counting or operation tasks with a student and then quickly enter the student's answer or strategy into the AMC Anywhere system, which will generate new tasks tailored to the student right on the spot, and the AMC Anywhere system will also provide a report to the teacher. The project's PD not only involved the AMC Anywhere tool, but it also helped the teachers think about conceptual instructional activities that made use of the data generated by AMC Anywhere and incorporating those into instruction and making data-based decisions. The PD was year-long, as I mentioned, and it entailed 72 hours, starting with 40 hours in the summer and then 32 hours throughout the academic year. It was a large-scale project with 65 schools spanning rural, suburban, and urban districts, 307 teachers, and over 5,000 students. The teachers who were included in the PD volunteered to do so and were selected by their administrators for inclusion. There was also a control group of teachers who were given access to the AMC Anywhere formative assessment system and used it during the year, but they were not trained or supported in using it. Note that the control group was not teachers who lacked the formative assessment tools. In fact, the control teachers were known to specifically use the AMC Anywhere formative assessment tool because that's what got them included in the control group, that there was this AMC Anywhere data. So it's just that they used it on their own. They didn't have the formative assessment PD support that the treatment group had. So after the school year, the researchers used multivariate analysis of variance to look at differences in student achievement scores on some AMC counting and number tasks. And they also used hierarchical linear modeling to look at the treatment and control groups in relation to school level and teacher level characteristics. The main findings were that overall, there was not a statistically significant difference between the treatment group and the control group with regard to student achievement. That's a bit surprising given the extensive 72-hour PD model. So is this a knock against the power of formative assessment? Not really, because there actually was a statistically significant positive relationship between the teacher's use of the formative assessment tool and their students' gains in achievement. It's just that positive relationship between formative assessment and student achievement, it spanned both the treatment teachers and the control teachers. It was their frequency of use with the AMC Anywhere tool that predicted higher student scores, not their inclusion or exclusion from the PD. So let's unpack that for a moment. What could be behind the finding that the use of formative assessment was statistically significant, but the PD on formative assessment was not? Speculating and interpreting a bit, it could be a feather in the cap of the control group teachers. They were using the AMC Anywhere tool on their own, and if they used it frequently enough, that might have been sufficient to realize the achievement gains that the treatment teachers were able to get. In this sense, it could also be a feather in the cap of AMC Anywhere as a tool. On the other hand, the overall finding could be a blow against the effectiveness of the PD, or possibly on the fidelity of implementation that the PD produced. The PD attempted to support the teachers in instructional strategies based on the formative assessment data, but perhaps the treatment teachers just used the formative assessment tool in the same manner that they would have used it even without the PD. making them very similar to the control group teachers, and there the prediction just comes from using the tool at all. Another couple possibilities that the authors bring up in the article are that there could be a ceiling effect with the achievement measure, because they looked at content standards that are part of the typical curriculum in kindergarten and first grade, so maybe it didn't stretch far enough in terms of the student gains. It also might be that there were differences between the treatment and control student achievements, but those differences might have occurred during the year instead of at the end of the year. And since the analysis relied on data measured at the end, any differences that happened along the way would have been washed out by the end of the year. The authors called for additional study to look during the academic year instead of just at the end. They also wanted to see more detail about how the teachers used the formative assessment data in their instruction, and not just whether they used the formative assessment tool. So there's some room for more nuance in the future. For me personally, I found this article interesting because I'm currently thinking about avenues for reaching teachers and spurring instructional improvement on a large scale. Although sustained, year-long professional development seems ideal, it is very difficult to scale up without a large source of funding. If, on the other hand, there are instructional tools or supports that we can put in the hands of teachers, perhaps via web-based platforms, and if teachers will naturally use them in effective ways, then that seems exciting from the perspective of scaling up. Although this article doesn't make any definitive statements on this topic, it has definitely given me some further things to think about and to discuss with colleagues. And before I go, I also wanted to say that this study had an additional finding that is kind of surprising, even though it's not unprecedented. They actually found that kindergartners outperformed first graders on several tasks in the study. I encourage people to read the full article if you're interested in this result, and it reminds me of conversations we often have here at Mizzou among the elementary team, where we discuss young children who are quite capable of solving rich problems, and that sometimes the process of learning school mathematics can inadvertently hinder them in some ways. But that's a topic for another study.